All right, y'all. We are looking at the topic 8 and 9 combined test review. And the first thing we have here is a question that's asking whether or not these triangles are similar. Now, we have seen diagrams that look kind of like this before. I'm going to see if I can recreate it on here. Something kind of like it. Okay, we have seen something like this before where we would have congruent angles, and usually when we've looked at these before, it would give us some information about congruent sides also. But there was something very particular that we had to remember about a diagram that looked like this, and that was something that was going on in this neighborhood right in here. Okay, right there in the middle of your picture, what I just highlighted in green over here is what we call vertical angles. From way back in the first semester, we talked about vertical angles, and we know that vertical angles in the middle of that picture are congruent to each other. So secretly, we don't just have one congruent angle that's marked, we have another one right there. And if you're looking at your notes talking about similar triangles, if you have two congruent angles, we automatically have a third congruent angle right up here that's also congruent. And if all three angles are congruent, then that is enough to say that those triangles are similar. So, yes, they are similar. Problem number 2, determine whether these rectangles are similar or not. Okay, so it's basically a true false question. Are these shapes similar? And so here's what we know about similarity. We know that the if shapes are similar, that means they have the same shape but a different size. But the sizes are related to each other proportionally. So when you look at the length of this side right here, the long side of the left triangle and the long side of the short triangle, you can set that up as a proportion. Okay, we can compare 24 compared to 16. And if we're doing it all correctly, if this is all going right, then 24 divided by 16 is going to be the same proportion as if we divided the short side by the short side, 10 divided by 6. Okay? If you punch both of those things into a calculator, you're going to see that 24 over 16, that is equal to 1.5. 10 over 6 is, well, honestly, it's just not. Okay, 10 over 6 is equal to 1.66 repeating. So, if that is the case, we have different proportions for our related side lengths, we would say no, they are not similar to each other. Question number 3 is pretty simple. Okay, you'll remember this from when we took the notes that the process for finding the geometric mean is really pretty easy. Okay, you're going to take your two numbers, 15 and 26, you're going to multiply them together, 15 times 26, and then take the square root. Okay, that is something you can plug into the calculator exactly as it is. Hit the square root, and then 15 times 26. The answer we get is it's about 19.7 roughly. And that's what we have right there, this option 19.7. There we go. Question number 4 is the exact same thing. Question number 4 is the exact same thing. We're going to do the exact same process. We've got our two numbers, 7 and 17. Multiply them and take the square root. And the square root of 17 times 7 is about 10.9. All right, go to our next one. Which of the following pairs of numbers do not have a geometric mean of 12? So this is one where we're actually taking the opposite approach. Instead of finding the geometric mean of a couple of numbers, it's telling us that the geometric mean is 12. And it's asking which of these does not fit that description. So what we're going to do is we're going to find the geometric mean of all of these. Square root of 10 times 13, square root of 8 times 18, square root of 9 times 16, and the square root of 1 times 144. That last one is pretty easy because 1 times 144 is just 144. So we know that one's going to be 12. So we know that that is not a good answer. We can do the same process for all of them. Okay, you can go 9 times 16 and take the square root, and 9 times 16 is 144, so that one's going to be 12. So that one's out. 8 times 18, you punch that in the calculator. That's also 144, so that's going to be equal to 12. The only option that's not equal to 12 is when you take the square root of 10 times 13. We get about 11.4. All right, that's going to be our answer because it does not have a geometric mean of 12. Question number 6. Find the value of x. All right, this right here is where we're going to talk about similar triangles. Now, we know from our notes that when you have a right triangle set up like this and you drop an altitude down, the big triangle on the outside, the medium-sized triangle on the left, and the small triangle on the right are all similar to each other. So here's what I'm going to do. I'm going to redraw two of those triangles. I'm going to redraw the medium one, and I'm going to redraw the small one next to each other here on my notes. Okay, here's the medium triangle, and here's the small triangle. Now we know, just looking at this diagram, that the long side, here, let me redo that one because I want to have a difference between the long side and the short side. Okay, so the long leg of the medium triangle here is 11. Okay, what we're doing is we're completely ignoring the small triangle here for just a second. Okay, the long side of the medium triangle is 11. The short leg of the medium triangle is 6. On the small triangle, completely ignore this stuff on the left for a second. On the small triangle, the long leg is 6. The short leg is x. That's our unknown. Okay? We have right here two triangles that we know are similar to each other. Let me put that little symbol right there in the middle. We know these triangles are similar to each other. So what we can do is set up our proportions the way we did on the problem a couple of minutes ago. Okay, we know that the long side compared to the long side is going to be 1 ratio, 11 over 6, and it's going to be the exact same proportion if we compare the short side to the short side, 6 over x. Both of these numbers on top came from the larger triangle. Both of these numbers on bottom came from the smaller triangle. We're comparing long side to long side, short side to short side. Okay? This is a problem where we're going to take it and we're going to cross multiply and solve. 11 times x is just 11x. 6 times 6 is 36. And to get x by itself, we just divide. 36 divided by 11. Not the most complicated thing in the world to punch in 36 divided by 11. We get 3.27 thereabouts. And it says to round it to the nearest whole number, so we're just going to call it 3. There we go. All right. Question number 7 is very similar to this one. It gives us that same diagram. It gives us a couple of the measurements. So you could take it and set it up the exact same way. Okay, that is something you absolutely could do, is look at your medium triangle and your small triangle, and you could write out all of these different proportions. You'd say that the long side of that one is 21, the short side is x, the long side of this one is x, the short side is 6. You could set up those proportions again. Okay, you'd be comparing 21 over x equals x over 6. Or you could note that this right here is the height of the altitude. And one of those theorems in your notes said that the height of the altitude is the same height, that length right there is the geometric mean of this piece and this piece. So if we just find the geometric mean of 21 and 6, take the square root, we end up with 11.2, thereabouts. All right. And actually, you're going to see what happens if we had gone through and solved this all the way through. We'd be cross multiplying. So we would have x squared equals 21 times, not 12, 21 times 6. And we would have to take the square root. So x equals the square root of 21 times 6. And it's exactly the same thing as what we just did right there. All right. So that's where that comes from. That's how we know that's going to be the height. It's the geometric mean of 21 and 6, those two little pieces right there. Question number 8 tells us that the polygons in this picture are similar to each other. Okay, I'm not going to redraw that whole entire thing. I'm just going to try and point to it with the mouse here. Okay, and then set up our proportions however they need to go. Polygons are similar. So that means there is a relationship. There is a scale factor that relates the side lengths of the smaller one to the side lengths of the larger one. And what happens is if you have a length of 5 right here and a length of 2 right here, there is a number that you can multiply to get from this 2 to this 5. And you can set it up as a proportion to find what that scale factor is. That's what we did in the notes. That's what we're going to do right now. Okay, 5 over 2, comparing the larger one to the smaller one. It's going to be the exact same proportion. That's 2.5, by the way. It's the same as if we compared this 10 and this 4, because those are the corresponding sides. 10 over 4 is the same thing. That's 2.5. And whenever you see this number over and over again, that 2.5, that is your scale factor. And so what happens is if we multiply a side on this shape times the scale factor, 2.5, it gives us the side length on this shape. So if we just take this x, multiply it times 2.5, or take this 6, take this 6 times 2.5, that's what's going to give us our x. So 6 times 2.5, that is equal to 15. 15 is our answer on that one. Question number 9 tells us again that these triangles are similar to each other, and it asks us to find the value of x yet again. Okay, so what we can do is just like last time. There's a relationship between these numbers up here and these numbers down here. We can find the scale factor to go from one to the other. Okay, here's what I'm going to do. We can set it up like this, 11.5. The corresponding side on the smaller one is 5. That gives us a scale factor, if you divide that out, of 2.3. Now, it is very tempting right here to just say, well, 25.3 and x are the ones that go together. So you're going to say 25.3 times the scale factor equals x. Well, here's the problem. If you did 25.3 times our scale factor, you end up with a number that is much larger than that. You end up with 58.19. Okay? Now, how would that make any sense that if this larger triangle has a length of 25.3, how would it make any sense that this smaller triangle has a length of 58.19? Okay? This is where we got to use a little bit of logic and we got to work around some stuff. We know that our scale factor going from the small one to the big one is 2.3. But what about the scale factor going from the big triangle to the smaller one? Because that's what we're actually going to need. If we did the scale factor the other way around instead, you could say 5 over 11.5. Or you could say 8 over 18.4. It should end up as the same number either way. That scale factor is a big old mess of a decimal. So we're going to ignore that. Actually, you know what? Scratch that whole thing. Okay, go back to our scale factor of 2.3, going from the small one to the big one, scale factor of 2.3. We're going to take that 25.3. Instead of multiplying times the scale factor, we're going to divide by the scale factor because that's what would do for us. Okay, we know that x times 2.3 equals 25.3. So if we want to know what x is, we have to divide by 2.3. That'll go away. and that's how we get x by itself. So that's what our x is going to be, 25.3 divided by 2.3. That gives us an answer of 11, a side length of 11. All right, question number 10, dilate the figure. All right, dilation, we found that when you're dilating around the origin, it's really pretty simple process. All you're going to do is you're going to take the coordinates and multiply times the scale factor. So I'm looking at L, M, and N. L starts off at 2, 4. M starts off at 6, 10. And N starts off at 8, 2. And what we're doing is we're dilating by a factor of 3 over 2. Okay, 3 over 2 is also known as the number 1.5. Okay, you can leave it as a fraction or you can do it as a decimal. Either way, what we're going to do is we're going to multiply times that number, times 3 over 2, or times 1.5, whatever floats your boat. Okay, all we're going to do is multiply those coordinates, the x value and the y value both. So 2 times 3 over 2 is going to give us a new x value of 3. 4 times 3 over 2 is going to give us a new y value, of 6. We do the same thing for m. 6 times our 6 times our scale factor gives a new x value of 9. 10 times our scale factor gives us a new y value of 15. Okay, everything is just getting scaled up times 1.5. New x value there will be 12, and our new y value will be 3. All right, so that's what we choose for L and M and N. We got 3, 6, we got 9, 15, and we got 12, 3. All right, this is more of the same. This right here, this problem is exactly the same as the last one. The only difference is it doesn't give us a graph. It just gives us a list of the points, which honestly is even easier because you don't have to find the points yourself. Okay, we've got A, B, and C. Their original locations are all given to us, which is just so convenient. And it tells us the scale factor is 1/4. So all you got to do is multiply all of those things, all of these values, times 1/4. So 1/4 of 16 is 4. Fourth is going to be 1. Okay, we're just multiplying all of the x values times 1/4. That's all it is. So we've got 4, 1. We've got 2, 3. And we've got 1, 2. Question number 12. Point is rotated 90 degrees clockwise. What are the new coordinates? So this is a time where it would be very helpful to open up our topic 8 notes. And on the topic 8 notes, you will notice what happens on the very back page on that chart that we filled out. You'll notice what happens when you rotate in various directions by various amounts. This tells us that we're going clockwise 90 degrees. If that is the case, we're going clockwise, then then our original xy, according to the chart, our original x and y value is going to turn in to y and negative x. Now that negative sign right there does not necessarily mean we're going to have a negative number. Okay, what it means is that we are going to take our original x value, and this number is going to be the opposite of our original. Okay, so what happens here is we swap places and we change the sign of our original x. Okay, so our original x and y is -5, +3. We're going to swap places, and we're going to change the sign of our original x. So our original x was -5. Our new x is going to be +5 right there. When we move it over, it becomes +5. This y value from our original one, the y value here, doesn't change at all. All right, so there we have it. +3, +5. Question number 13. This one's about composite transformations. All right, you remember that word composite means it's made up of two things at a time. Okay, the point 3,7 is having more than one thing done to it. We start off at 3,7, and then it's reflected over the x-axis. And then it's translated and gives us the notation for that translation. So in your topic 8 notes, you can see what happens when you do a reflection over the x-axis. Okay, when you reflect over the x-axis, something happens to your coordinates. Okay, what you're doing is you're going from the top of the graph, flipping straight down to the bottom. Okay, imagine that in your mind. You're taking this point, you flip it straight down to the bottom. So what happens is that your original coordinate, your x coordinate doesn't change. Okay, your x coordinate stays exactly the same because when you flip over in a vertical way like that, there is no movement side to side. So the x will stay the same. But the y value is suddenly going to become the opposite of what you started with. So after we do this the first time, it's going to become 3, -7. That's our first transformation. After we've done that, it tells us that there is a translation. Okay? That's our first change right there. Our second change is a translation where we take the x values and subtract 2, and the y values and add 4. So if we're subtracting 2 from the x, it becomes 1. If we add 4 to the y, it becomes -3. And there we go. +1, -3. Question number 14 is another dilation, and actually it's another composite question because it's got a dilation and it's got a rotation. All right, so we start with the dilation. It gives us our scale factor right there, and we know that our original point is right here. And what we're going to do to dilate is multiply both coordinates times the scale factor. And that's something you can do in the calculator, or you could just recognize that 0.75 is 3/4. Either way, it'll get you the right answer. It'll get you where you need to go. And if you're doing that, our first transformation brings us to right here. Our dilation turns it into 3 and -9. Then what we're going to do is rotate 180 degrees. So back on your topic 8 notes, and this would be something that's good to add to your cheat sheet. On your topic 8 notes, when you rotate 180 degrees, the x and y's do not swap. But we do change both positive negative signs. All right, so after we do that transformation, +3, -9 is going to turn into -3, +9. And that's where we end up, -3, +9. Our last one, we're doing another dilation, and it's asking about a specific point that we start with. And it's asking what is the new image after we have dilated by a factor of 2.5. Okay, it's just like we've already done. Take the x and y values, of our original. Multiply everything times 2.5. So negative 8 times 2.5 gives you a new x value of negative 20. And positive 6 times 2.5 gives you a new x value of positive 15. And there we have it. All right, that is everything on our test review. If you have any questions, please let me know as you're working through it. And y'all have a good day and study up and do well on this test. All right, y'all have a good one.